Hello, and welcome to a new module on derivatives. Today we will be reviewing the concepts of concavity, inflection points, and the second derivative criterion. The requirements are relatively simple, although they may appear extensive. You just need to be familiar with the derivatives of elementary functions, understand what constitutes an extremum in a function, maximum and minimum, know how to calculate intervals of growth and decay, and have a grasp of basic mathematical operations. Now let's begin by exploring the concept of concavity. The following definition is sourced from the book Calculus by Larson. We'll explore an alternative perspective later. Consider f as a differentiable function on a given interval, I. We describe the graph of f as concave up when the first derivative is increasing within the interval, and as concave down when the first derivative is decreasing on the interval. This definition might seem unusual, as we're used to other definitions. We'll introduce an alternative, which is as follows. This alternative approach indicates that a function is concave up when its graph lies above the tangent lines and concave down when the graph is positioned below the tangent lines, as you can see written here. It can still be complex because determining whether a function is concave up or concave down requires a graphical representation. Let's see how this would look like. In this illustration, I've used the function x squared, which is represented by the parabolic curve, indicated by the thick blue line. Additionally, I've depicted thinner lines as tangent lines at various points on the parabola. As you can observe, all the tangent lines are situated below the function's graph, indicating that the graph of this function is in this case concave up. When we represent the same parabola but with a negative sign, minus x squared, we notice that the function remains the same, represented by the thicker blue line, while the tangent lines are all positioned above it, as evident in the graph. In this scenario, the graph of this function would be concave down. As I mentioned earlier, do we always need to plot the function to determine whether it's concave up or concave down? The answer is no. We can rely on a theorem known as the concavity criterion, which states the following. Let's consider a function for which the second derivative exists within an interval. In that case, if the second derivative is positive for any x within the interval, the graph is concave up, and if the second derivative is negative for any value within that interval, the graph is concave down. What procedure are we going to follow? It's quite easy. First, we attempt to identify the values at which the second derivative is either 0 or does not exist. Then, using these values, we divide the real number line into intervals. In each of these intervals, we examine the sign of the second derivative to determine when it's positive and when it's negative. Through this analysis, we can deduce whether the function is concave up or concave down. Let's see an example. Let's take the function f of x equal to 6 over x squared plus 3. We'll identify where the function is concave up and concave down by examining the second derivative step by step. First, I'd like to point out that the function is continuous at all points. If you examine the denominator, which can be a concern, in this case, it's x squared plus 3. It's important to remember that the square of any real number is always positive. So regardless of the specific number used here, when squared, it remains positive. Furthermore, adding 3 to it will never result in 0, unless we venture into working with complex numbers. However, for our purposes, we'll assume we're working with real numbers and seeking real values. So, the denominator never equals 0, which means the function is defined at all points and maintains continuity throughout. In this case, it's a polynomial quotient, and such functions are consistently continuous. Let's proceed to determine the first derivative. To find the first derivative, I've employed a somewhat unconventional technique. I've taken the denominator and reciprocated it with a negative exponent, a permissible step. This approach alters our method for finding the derivative. If you prefer to proceed directly, you can use the quotient rule, but I've set aside the quotient rule for later practice, as we'll utilize the chain rule in this method. So, what is the derivative? The exponent, which was initially minus 1, is brought down and multiplied, which is why I've indicated minus 6 here. Then we subtract 1 from the original exponent, which was minus 1, resulting in minus 2. The x squared plus 3, for now, remains undifferentiated. Next, we multiply it by the derivative of x squared plus 3. Let's make a slight adjustment. You'll notice that I have 2x here, and it moves to the front. So we end up with minus 12x times x squared plus 3 raised to the power of minus 2. Now we've reached this expression. Typically, we don't work with negative exponents, so I'll rewrite it in fraction form to make it clearer. It's essentially minus 12x divided by x squared plus 3 squared. You should arrive at the same result if you were to apply the quotient rule directly to the original function. Alright, the first step. We've successfully calculated the first derivative. Now let's move on to computing the second derivative. To do this, I've applied the quotient rule. Observe that the derivative of the numerator is minus 12 times the denominator without differentiation, as you can see here. Hence, it's minus 12 times the derivative of the denominator. However, the numerator without the derivative is minus 12. Consequently, when differentiating, the minus sign in the original rule results in a plus sign. The next step is to multiply this by the derivative of the denominator. What is the derivative of the denominator? The 2 comes down in front, leaving x squared plus 3 as it is, and it's raised to 2 minus 1, which is 1. Then we multiply it by the derivative of the interior, which is 2x as indicated here. This is the derivative of the denominator. Furthermore, all of this is divided by the denominator squared. It might seem like a rather difficult expression, but it can be simplified fairly swiftly. If you observe, you have x squared plus 3 in both of the terms. You can extract the common factor and eliminate it with one of the terms in the denominator. In that case, you would end up with this expression divided by x squared plus 3 cubed, as I've simplified one of them. I hope the simplification process doesn't pose much of a problem. Now, I just need to make an adjustment to the numerator. Here, it's quite easy. Subtracting 12x squared from 48x squared leaves us with 36x squared, and then I have minus 12 times 3, which equals 36. I can identify a common factor. In any case, the simplification isn't very complex, so I encourage you to give it a try. If you encounter any difficulties, please don't hesitate to reach out to me. I've now obtained the second derivative. Let's set the second derivative equal to 0. In this case, we have this expression. 36 times x squared minus 1 divided by x squared plus 3 cubed equals 0. Similar to before, the second derivative poses no issues. It is defined at all points. Why? Because, just as before, the denominator never equals 0, making it perfectly valid. Hence, we don't need to add any more points to the ones we are about to calculate. We shall proceed with the process. I have one quotient equal to 0. This implies that if the quotient is 0, it's because the numerator is 0. Therefore, this part right here, 36 times x squared minus 1, must equal 0. The 36 is a constant that's being multiplied, and when moved to the other side of the equation, it becomes a divisor. 0 divided by something results in 0, unless we are dealing with 0 divided by 0, which is a different scenario. In this case, 0 divided by 36 gives 0. Now we're left with just x squared minus 1. Clearing this is easy. The minus 1 is moved to the other side, and by taking the square root of both sides of the equation, we end up with x equals plus or minus 1. I hope you've also become proficient at these simplifications. We already have 2 points for which the second derivative is 0. As mentioned earlier, we don't need to introduce any additional points. Adding more points would be necessary if the second derivative was either undefined or non-existent. In this case, the second derivative is defined at all points, so we only have plus and minus 1 to consider. What comes next is dividing the real line into 3 segments. Why 3? Because we have 2 points, the minus 1 and the plus 1. So the division of the real line looks like this. From minus infinity to minus 1, from minus 1 to 1, and from 1 to plus infinity. It resembles any real number line, but with the 2 points removed. What's the next step? It's to examine the sign of the second derivative in each of those intervals. To do so, we need to choose a specific value within each interval. Since the second derivative only changes sign at minus 1 and 1, it will maintain the same sign within each of these intervals. Therefore, selecting a particular value from each interval will suffice. How do we go about it? Well, I've chosen minus 2 from the first interval, 0 from the second interval, and 2 from the third interval. Next, we'll evaluate each of these test values in the second derivative, using the expression at the top. Without using an equal sign, of course, we'll assess whether it results in a positive or negative outcome. Although I haven't included the actual calculations, I've indicated the sign corresponding to the solution. When I substituted x with minus 2 in the second derivative, I obtained a positive result. For x equal to 0, I got a negative value, and for 2, I obtained a positive number. I emphasized that it's simply a matter of taking this function, substituting the chosen values for x, and determining if the result is positive or negative. Once we know the sign of the second derivative in each interval, the next step is to determine whether it is concave up or concave down. In this case, we find that it is positive, indicating concavity upwards, then negative, indicating concavity downwards, and finally positive again, indicating concavity upwards. The graph illustrates this. The points where the concavity changes are at minus 1 and 1. The second derivative is 0 at these points. Up to minus 1, the function is concave up, as the tangent lines lie below the curve. From minus 1 to 1, the tangent lines would go above the curve, indicating concavity downwards. Beyond 1, the tangent lines would be below again, implying concavity up. The graph of the function visually represents this behavior. A definition. We refer to inflection points of a function as those points where the concavity changes direction. As we discussed earlier, there are inflection points at -1 and 1 where the function transitions from concave up to concave down. Note that this definition may vary among authors of different textbooks. Some may require the presence of a tangent line at these points, while others do not. I include this information to illustrate the variations in the definition of inflection points. Let's proceed with a theorem that guides us in locating inflection points. If C is an inflection point on the graph of f, then either the second derivative of f at c equals 0, or f is not differentiable at x equal to c. Let's illustrate this with an example. Let's consider a function f of x, which is a straightforward polynomial, x to the fourth power minus 4x cubed. It's a polynomial that's easy to differentiate and analyze without any continuity issues. Now, let's go through the entire process of finding the inflection points. We'll need to take two derivatives. Since it's a polynomial, this is a straightforward process. First, the first derivative. The 4 comes down as a coefficient, and I reduce the exponent by 1, so I have 4x cubed. Then, the 3 comes down and the second exponent is reduced by 1. This results in 4x cubed minus 12x squared. The second derivative is also straightforward. The 3 comes down and multiplies by 4, leaving us with 12x squared minus 24. What did I do? I simplified the second derivative a bit by factoring out the common factor of 12x. I ended up with 12x times x minus 2, as you can see. Always double check your work when factoring out common factors to ensure accuracy. When I multiply 12x by x, I get 12x squared, and when I multiply 12x by minus 2, I get minus 24x. We set the second derivative equal to 0, resulting in the expression 12x times x minus 2 equals 0. In this case, for two factors to multiply and equal 0, either one of them must be equal to 0, or the other must be equal to 0. So, we have no further issues. We then need to divide the real number line into three segments, from negative infinity to 0, from 0 to 2, and from 2 to positive infinity. In these intervals, we will analyze the sign of the second derivative to determine whether the function is concave up or concave down. In the first step, we selected the test points as -1, 1, and 3, which are intermediate points in each of these intervals. When we evaluated the second derivative at these test values, we obtained positive, negative, and positive results. To do this, you would substitute -1, 1, and 3 into the second derivative expression. This means that the function changes from being concave up to concave down, and then back to concave up. The inflection points are 0 and 2, as the concavity changes at these points. You can see these points on the graph. At 0 and 2, the concavity switches from being concave down to concave up, if I recall correctly. A note to consider is that the reciprocal of the theorem we discussed is not true. For instance, if we take the function x to the fourth, its second derivative is 0 at x equals 0. Of course, if we take the second derivative, we get 4x cubed, and the following one would be 12x squared. When we set the second derivative to 0, we find x equals 0. However, the point 0, 0 is not an inflection point, as the graph remains concave at both before and after 0. It resembles a parabola. Therefore, it's essential to recognize that the theorem's reciprocal is not generally valid. What else can we use the second derivatives for? There's a highly significant theorem known as the second derivative test, which enables us to categorize a function's extrema based on the second derivative. Let's select a function for which f prime of c equals 0, meaning c is a critical point, and the second derivative also exists in an open interval containing c. Then, if the second derivative at c is positive, f of c is a relative minimum, and if the second derivative at c is negative, f of c is a relative maximum. What if f of c is 0? The criterion can't decide, so we would need to use the first derivative criterion. Here's a quick example of a simple polynomial, easy to differentiate and work with, defined at all points without any continuity problems. We find the critical values of that polynomial. Do you remember how they were found? By equating the first derivative to 0 and solving for x. Also note that in this case, we don't need to add any more values, because the first derivative is defined at all points. Here's the first derivative, which is straightforward. You can see that the 5 comes down, the 3 comes down, and you can factor out the common factor of 15x squared. This leaves you with 15x squared times 1 minus x squared equals nil. The critical points can be found by setting the equation to 0. So either x equals 0 or 1 minus x squared equals 0. Solving the second equation, we get x equal to plus minus 1. 3 critical values. Let's classify the critical points using the second derivative. Up to this point, we've been using the second derivative criterion. How is it done? Well, first, we calculate the second derivative. Since it's a polynomial, it's quite straightforward to differentiate. In fact, I've already differentiated it. It simplifies to 4 times minus 15, which equals minus 60 times x cubed plus 30 times x. Now, let's evaluate the critical points we obtained earlier with the second derivative. We find that for minus 1, the second derivative is positive. For 0, the second derivative is 0. And for 1, the second derivative is negative. By applying the second derivative criterion, we can conclude that at minus 1, we have a relative minimum because the second derivative is positive. At 1, we have a relative maximum because the second derivative is negative. For 0, the criterion is inconclusive. So we would need to apply the first derivative criterion for that point. This is summarized in the table, and we classify the critical points by dividing the real line into intervals and studying the sign of the first derivative in each of those intervals. I've taken the intervals as we derived them, going from minus infinity to minus 1, from minus 1 to 0, from 0 to 1, and from 1 to plus infinity. I've chosen arbitrary values within each corresponding interval, calculated the first derivative at these values, and found that it's decreasing, increasing, increasing, and then decreasing again. As you can see, at the point 0, we indeed have an inflection point. It's neither a maximum nor a minimum in this case. The graph of the function exhibits a minimum, a maximum, and an inflection point like this. In this unit, we learned about concavity, inflection points, and the criterion of the second derivative, which will be used a lot. Thank you for your attention.